like to thank the organizers as well for this opportunity to remember Eric and to give this talk. And before I begin, like Benno, I'd also want to posthumously thank Eric, because Eric was in some ways my starting point in type theory when he let me come to Stockholm and work on formalizing things with the E categories that Peter mentioned this morning, Peter talked about this morning, when I was just a master's student. So without that, I would probably not be here giving this talk, and I may never have gotten interested in type theories. And there's a second reason why Eric is important for this talk. It's because what I'm going to talk about today is something that Peter and I discussed and worked on as a direct consequence of some of Eric's work, namely his paper on DFOL, or I think at one point he called them fold signatures. And a question that I asked him, which was about some kind of monoidal substitution product for his DFOL signatures. Anyway, so for many reasons, what I'm going to talk about today is directly a consequence of things Eric did. Right, so my talk today, I'll try to present a point of view on dependently typed theories as generalized Lawvere theories. In what sense? Well, let me begin by just recalling what algebraic theories are. So multi-sorted algebraic theory is the data of a set of sorts, a set of function symbols that are typed using these sorts, and a set of equations on terms of the term algebra over these function symbols which have the same type. Right, so this definition is the good old familiar one of multi-sorted algebraic theories. So, I mean, there is a question that has been worked on for a long time, for decades, for, I mean, I suppose more than 40 years now, if you, count my which is that how does one take this definition and try to think of it in a context where sorts can depend on one sort can depend on another. So what should a dependently sorted algebraic theory is? And there are many syntactic approaches to this, and I've listed some of them here. And there are others that I know less well, including answers to this question, which are formulated internal to type theory, like quotient inductive types. But what I'm going to present today is a strictly less general definition than all of the previous ones. But why do I find it interesting? It's because it is quite well behaved. It's well mannered. It resembles algebraic theories from the point of view of category theory extremely closely. And in fact, it's not even something that's very new. It is defined in Fiore's short Licks paper, and he calls it sigma zero models with substitution. So what I call dependently typed theories are precisely what Fiore calls sigma zero models with substitution. But I'll try to present them in a slightly different way. So I learned this from Marcello Fiore a little less than a year ago. And I wish I had known, I had read his paper earlier. Okay, so before I start talking about dependent sorts, let me give you some standard definitions of algebraic theories using a categorical framework. So here are some equivalent categorical definitions of algebraic theories, and most of you are probably very familiar with this. So let S be a set, then an S-sorted algebraic theory is a category with finite products whose objects are freely generated in a suitable sense by the elements of S. Now the definition is that an S-sorted algebraic theory is a finitary monad on the category of sets over S, right? The category of presheaves over S. Now if you let fin S be the category of finite sets over S, So its objects should be thought of as finite contexts of variables that are typed by elements of S. Then the presheaf category so the category of covariant presheaf from fin S cross S to set is the category of Cartesian S-sorted term signatures, in that given a finite context of S-sorted variables and a sort in S, the presheaf gives you the set of term symbols that are sorted, or function symbols that are typed by that context and that sort. And this category has a substitution monoidal product and an algebraic theory. An S-sorted algebraic theory is then a monoid in this monoidal category. Right. So all these definitions have an underlying combinatorial picture, which is based on seeing the terms in an algebraic theory as being obtained by grafting function symbols of the algebraic theory and variables in a Cartesian way, which has to do with the fact that we can throw away or duplicate inputs of these corollas. And so a term or a term symbol, if you like, in a multi-sorted Lawvere theory looks like an operation that takes a finite coproduct of sorts as an input and has an output sort. And this is why Cartesian S-sorted term signatures are objects of this presheaf category. Right, so this is the setup that I'd like to generalize to dependent types. Okay, right. And I'll begin with a syntactic definition. So dependent type signature is a set that's graded by the natural numbers, such that each Sj is a set of type declarations over the coproducts, over the signature that's obtained by taking the coproduct of all the previous Si. And you can reassure yourself that that's also a signature thanks to this definition. And what is a type declaration? So that's a mutually inductive definition. A type declaration over a signature is a pair of a context that is typed by the signature S and a fresh type symbol. So essentially introducing a new type symbol that is typed by a context of the signature. So I'm not going to get into details about what contexts of a type theory are, but all of this is just in the standard Martin-Löf way of defining what contexts of a type theory are. Okay, so here are a couple of examples, which is always better than looking at definitions. So here's a simple one. It's a signature such that S0 has a single type. So ob is a type. And here you have a context, the only context over the empty signature. And S1 has a single type as well, which is typed over hom, which is typed over the context, which has two variables of type ob. And here's another type signature. You have S0 is once again a singleton. It has just the type declaration C. And S1 has, for every natural number k, type declaration O in the context of variables x1 to xk and another variable y of type C. So, of course, these correspond to the signatures for directed graphs on the one hand, and planar collections, colored collections, if you like, on the other. Right. So given a type signature, we can define what's called its category of contexts, or its syntactic category, whose objects are contexts that are typed by the signature S, and whose morphisms are context morphisms in the usual sense. And since we don't define any term symbols, a type signature consists only of type declarations, it's easy to see that all morphisms, any context morphism can contain only variables. And given a signature S, I'll define CS to be the full subcategory of its category of context, that is its syntactic category, on signature, on the context, sorry, of the form gamma extended with a variable of type A for every type declaration of the form gamma A in S. Right, so the objects of the category CS are in bijection with the elements of S. So here I'm going to open a small parenthesis to give some terminology. So a small category is direct. I'll say this is a standard definition. If it has no infinite descending chains of non-identity morphisms. So descending in this sense, so C is related to D if there's a non-identity arrow from C to D. And a category is locally finite if each of its slice categories is finite. So the first observation is, and which is an extremely agreeable one, and it's not new, it's this is part of Mackay's work on folds, is that given a signature S, CS op is a locally finite direct category, and the map taking a signature to S to CS op is an equivalence in a suitable sense between signatures and locally finite direct categories. So this allows us to define a type signature or to recognize type signatures in the wild simply by recognizing locally finite direct categories. And here are some examples, some well-known examples. So any set, of course, is a discrete category. It's a locally finite direct category. The category with two objects and two parallel non-identity morphisms between them. The category of globes, the category of semi-simplices, the category of planar corollas or planar elementary trees, the category of planar trees, the category of opitopes. All of these are locally finite direct categories, and I'm probably forgetting a couple. Let's see, there's also the full subcategory, for instance, of globular sets on the pasting schemes. That is also locally finite and direct. Right, so there are several of these categories that are well known and that, in fact, thanks to this observation, correspond to dependent type signatures. Right, so now that we have an agreeable, nice notion of what a dependent type signature is, let me try to define what a dependently typed theory is. And here I'm going to give you a slightly imprecise definition. But it's sufficiently precise that those of you who are used to type theory should be able to fill in the details, and it's sufficiently imprecise that those who aren't used to type theory shouldn't be frightened by this definition. So a dependently typed theory consists of a dependent type signature, an ordered set of term declarations, and an ordered set of equations, and the order has to do with this little substitution appearing over here. And there is a small subtlety to note here, which is that gamma is a context. In each of these rules 2 and 3, gamma is a context typed by S. In other words, gamma, as none of the types in gamma contain any of the terms declared using the declarations of the dependently typed theory. So gamma contains, all of the types of gamma contain only variables. So this is a subtlety to note. This means that there's no induction when there is in this definition. Okay. Right. So once again, an example is nicer than the definition. Here's an example of a dependently typed theory, the theory of categories. It has two type declarations, the same as before. Two term declarations for identity morphisms and for composition, and three equations between typed terms. So two for identity morphisms and one for associativity of composition. And in fact, we'll see that there are dependently typed theories. There's a general way of recognizing dependently typed theories, and there are dependently typed theories of two categories, n categories, omega categories, reflexive graphs, and lots of other things. Right. So here's the categorical definition. So let S be a locally finite direct category, and let fin S be the category of finitely presentable presheaves on S. So when I say presheaf, I mean contravariant set-valued presheaf. And of course, finitely presentable presheaf is exactly a presheaf that can be written as a finite colimit of representables. And for every representable presheaf, there is what I'll call the boundary subrepresentable, which is a sub-object that's got by taking the colimit over this full subcategory of the slice category. Right? And this is also a standard definition. And since S is locally finite, the boundary of every representable is finitely presentable. It's a finite colimit of representables. And I'll say that a finite cell complex is a finite sequence of chosen push-outs, so in presheaves, of chosen push-outs of boundary inclusions. So once again, a finite cell complex is a finite sequence of morphisms in presheaves on S, where each morphism is a chosen push-out of some boundary inclusion. And when I say chosen push-out, I mean that the push-out square is part of the data. Of course, it's not difficult to show that a presheaf on SS being locally finite direct category is finitely presentable if and only if there exists a finite cell complex that ends in X. And so we define this category of cell complexes over S to be the category whose objects are finite cell complexes and such that a morphism between two finite cell complexes ending in X and ending in Y respectively is just a morphism of presheaves between X and Y. And this slightly, what I'm looking for anyway, the slightly convoluted definition serves the following purpose. Clearly, there's a forgetful functor from finite cell complexes to finitely presentable presheaves, which is an equivalence of categories. But the important thing to note is that the opposite category of finite cell complexes is isomorphic to the syntactic category of the type signature S, so which is the reason for defining this category of cell complexes. So essentially, a finite cell complex is just an extension of contexts with types from the signature. As a corollary, we have that the opposite category of finite cell complexes is a contextual category. In fact, it's a free contextual category generated by this over the signature S. Right. So I'll say that the category of Cartesian S-sorted term signatures is the following functor category. It's the category of functors from finite cell complexes on S to presheaves on S. And the idea is that a finite cell complex is a context over the signature S, and a Cartesian S-sorted term signature is it's a presheaf that gives you for every context and a type a set of term declarations. And this is functorial in the right sense. That this is what corresponds to the rules that I gave for the syntactic definition of dependently typed theories. Right. And here's another categorical parenthesis. So given a small category and the category of finitely presentable presheaves on the category, then the functor category from the category of finitely presentable presheaves to all presheaves, so has a substitution monoidal product, which is just corresponds to the composition of finitary endofunctors. That's defined in this way, and whose unit is the inclusion functor from finitely presentable presheaves to all presheaves. Um, and left-Kahn extension along the inclusion functor from finitely presentable presheaves to all presheaves is fully faithful and monoidal in that it sends the substitution product of two of these, what I like to think of as collections, to a composition of endofunctors. What this means is that there is an equivalence of categories between monoids in this category of functors and finitary monads on presheaves on C. So what that little interlude tells us is that we have a substitution monoidal product on Cartesian S-sorted term signatures, and the term algebra of a Cartesian S-sorted term signature is just the free monoid on X. For the same monoidal product that's defined here. Right. And an S-sorted, and now finally with this setup, we can give a categorical definition, and in fact, we give three equivalent categorical definitions of an S-sorted dependently typed theory. And the first one is that it is a monoid in the category of S-sorted Cartesian term signatures. The second is that it is a finitary monad on presheaves on the type signature, seen as a locally finite direct category. And the third is that, and this is something that I haven't mentioned, but that is for want of time, the third is that an S-sorted dependently typed theory is an S contextual category. So an S contextual category is a contextual category with some extra structure on it, which basically comes from the idea that all of its objects are defined by declarations in S and substitutions given by the term declarations. And this last definition is the one which correctly generalizes the finite product category definition of usual multi-sorted algebraic theories. Okay, and these definitions also have an underlying combinatorial picture, which is also Cartesian grafting of trees, except that here trees or even operations or corollas are no longer things that take as an input a finite set of points and have a point as output, but they take a finite cell complex as input and have cells as output. And so grafting these operations together is grafting cells onto cell complexes. And this point of view is really, it's not new, it's something that's quite old. This is the point of view behind Albert Bironi's T categories and Bironi-Lenzed T operads. Right. So this definition, this rather elegant definition of dependently typed theory, allows us to recognize many dependently typed theories in the wild. So every multi-sorted algebraic theory, of course, is a dependently typed theory. There are dependently typed theories of directed graphs, of globular sets, of semi-simplicial sets, of planar collections, colored collections, of planar dendroidal sets, of planar optotopic sets, of not planar, of optotopic sets, of categories, of colored planar colored operads, of simplicial sets, of strict omega categories, of weak omega categories, and in fact, if you have any finitary Cartesian monad on presheaves on a type signature, every T operad is a dependently typed theory. So this is quite reassuring that this definition, even though it may not be the most general syntactically, allows us to recover quite a few examples. Okay, and so this is the main result, if you like. At least for the moment, this is still a work in progress, which is that we have equivalences of categories between the category of S contextual categories and the category of monoids in Cartesian S-sorted term signatures, the category of finitary monads on S, and the third statement can be rephrased using the terminology of Lawvere theories with arities. So I think I have about 5 minutes left. And so to sum up, we introduce a definition of dependently typed theories, which nicely generalizes the usual definition of multi-sorted algebraic theories. And these, which can be seen as Cartesian dependent multi-categories, are perhaps less expressive than other syntactic definitions of what dependently typed algebraic theories are, but at least they have a nice category theoretic description, nice category theoretic descriptions. And we see that we have a large number of well-known examples, and some people have actually taken the trouble to work out explicit definitions of the syntactic definitions of these type theories. Like, I know that there are some definitions of the type theory of globular sets, the type theory of strict omega categories, of weak omega categories, and a couple others, and optopic sets as well. Right. So in the couple of minutes that I have left, I'm going to talk about what a linear version of something like this should be. And I'll use I'll use planar colored operads to motivate this. But to begin with, if one looks at a term of a multi-sorted algebraic theory, one can say that it is linear if so a term in the context gamma and whose sort is A, if each variable of the context gamma appears exactly once in T and in the same order as in gamma, right? That's what I'll say is linear. This may be slightly stronger than what some people think of as linear. So if you don't think of this as linear, think of it as planar. A multi-sorted algebraic theory is strongly regular if each of its equations is between linear terms. So in each equation, each variable in the context appears exactly once in the same order on the left and on the right. So for example, the theory of semigroups is strongly regular, but the theory of commutative monoids is not, right? Because in commutativity axiom, X and Y are interchanged. Right, so there is a close link between strongly regular theories and planar colored operads. And it basically goes as follows. If you have a set of sorts or colors in the lingo of operads, then you can take the set of finite lists of elements of S, and then the category of linear S-sorted term signatures is just the slice category of S over the set of finite lists times S, the product of the set of finite lists, and S. And this category, this functor category, has a linear substitution monoidal product, which is the grafting of trees and which is defined using the usual day convolution given by the monoidal product on sigma S. Right, so this definition may look a little, I mean, it is a standard one, but basically what it does is to say that given a term signature, a linear term signature X, this set is the set of linear substitutions or linear context morphisms from the context of this, so this list of types to the context which is this list of types using terms from this signature. That's what it is. And then you can we can define the monoidal product in a general way using this. And this is just the combinatorics of grafting planar labeled trees without any Cartesian grafting, just usual grafting of planar labeled trees. And then you can say that a planar operad, an S-colored planar operad, is a monoid in this category of collections. And it seems as though, now this is really the point at which I'm going to wave my hands, because this is something that I've just been thinking about not for very long. It seems as though there is a category. I don't want to say things that are wrong, but it would seem that there is a category sigma S for any dependent type signatures, and a kind of convolution operation, which instead of using finite lists or finite coproducts, if you like, uses a kind of finite co-limit or a formal finite cell complex, if you like. And if you look at these two equations here, this definition and this one, you see that the product here in the Day convolution is replaced by this end over the category of elements of some finite cell complex gamma. Anyway, so this is something that I've been thinking about. And I don't know if this gives you a monoidal product and a notion of dependently colored ocrad. And so I'm going to leave you with this question. And I'll thank everyone and stop here. Thank you.
So let's thank Chaitanya. And we open the floor for questions.
I'm not sure if I can see the chat.
Hi, you may have mentioned.
Oh, I have it.
Sorry, go ahead.
No, go ahead. Go ahead.
I think
I'll be last.
you said this. You may have said this already, but so what's an example? You said this is less general than other notions in the literature. Do you have like an example that distinguishes?
Yes. Now this is where a blackboard would be useful, but I think I can probably get one up. Hang on. Let me share external page. So here we go. So let's say you have a signature where you have O as a type, and M is a type in the context XY of type O. Let's say you have a constant of type, I don't know, star, a constant star of type O, right? So this is a term declaration. These are your types. These are your term. This is your terms here. And now let's say you have a term declaration for all X of type O, M of type X star. You have, let's say G here. You have something over here. I don't know, let's say some circle GG, something of this. Like I can write this, right?
Would this be something like defining the terminal element of a category, for instance, where you would need to make a morphism from anything into the terminal?
Yeah, so when you're defining a terminal element of the category, then you would have some kind of equation which would use something of that. Actually, no, I think no, defining the terminal element of the category should be okay, because you get only the terminal object here. You won't get it in the context, but you get it on the right-hand side, right? That's okay, because you're allowed to have a substitution here, but not in the context. But something like this would not be possible. You have to have only variables on this side in the context. That's the syntactic caveat.
Okay, thanks.
More questions? My question was answered now, because that was my question. So.
Yeah, I would have a question. Maybe it was also answered, but maybe just to clarify, can your notion of dependent algebraic theory represent all essentially algebraic theories, or was this the counterexample?
At least I don't think it can. I'm not sure, but I don't think it can. Yeah.
I see.
I don't think it
should. In particular, the syntax of type theory or categories with families themselves are also, as I understand it, because, so in type theory, you define all syntactic classes mutually inductively.
Yeah.
And in your setup, you seem to be straightening out at least part of it and have first a layer of types and function symbols, and then the axioms come later. And I was wondering whether how strong this is.
Yeah, so even the function symbols come after having defined the types. So in some sense, you're not
right. First sorts and types, and then function symbols and equations.
So yeah, but I do think that if you're talking about the essentially algebraic theory of, let's say, contextual categories, for instance, maybe you may be able to, maybe it is an essentially algebraic theory that can be defined as a type theory in this sense. I'm not sure how to think about it, but maybe it is.
Thank you.
Any more questions? If not, then we thank Chaitanya again.